So I'm quite disappointed of having only 11 answers, but well, I would like to know why I get only so few answers, but maybe I will find out one day. I have another 2 questions for next week. The first of them is mandatory because it's not a question on natural language processing or linguistics, it's a question on the class. So I would like you to give me your opinion on the class as it happened this year. And the second one is a question on natural language processing, but the first one is mandatory. Okay, so the questions you answered, the first one was about an ontology. And my colleague Serge Garlati usually takes motorcycles as a paradigm for ontologies. And of course, motorcycles are much easier because they have pieces, and these pieces are assembled, and pieces have some reason of being, some functionality. And so it's very mechanical, and it's quite easy to imagine an ontology of a motorcycle. I took an abstract notion and even a very abstract and very human notion, the notion of hope, to make you think about what an ontology is and how we can approach something such abstract as hope. And the results are manifold. So since there are only 11 answers, let's take them in order. So Andres says, according to Wikipedia, hope is a state of faith, an optimistic mood. Okay. Now, this is not an ontology, this is a definition. I know that Wikipedia is a formally structured resource, but this doesn't make your answer an ontology. And I specifically asked for a domain for concepts and relations. So you don't give us neither domain, neither concepts nor relations. So I'm not saying what you have written is wrong. I'm only saying it's not an answer to the question I asked. Camille uses as a domain the domain of states of mind. Okay, so that's fine, but what is a domain? A domain is a set in which our formulas, either in first order logic or in description logic, in whatever formalism you choose, our formulas are interpreted. Okay. So this means that for all predicates in our formulas and for all constants, we need objects in the domain. So if you say, I'm taking the domain of states of mind, then all the elements in your domain are states of mind. And then you can compare states of mind between them. You can say this one is a subcase of that one, this one is the opposite of that one. Okay, that's correct, but maybe not extremely useful because we want also the agent. So who has this state of mind? A human. And if I want to draw a relation between humans and states of mind, then in my domain, I need to have also humans. So what Camille says is correct, but it's maybe a bit restrictive, and this is a very restrictive set, the domain of states of mind. And when she says, I would like to draw links between hope and concepts such as expect, desire, goal, or motivation. Okay, desire is maybe a state of mind, but it also is an emotion, and goal is maybe not a state of mind. So she is contradicting in some sense. Christian says domain of feelings, and concepts emotional state. Now here, this is a contradiction. An emotional state is not a feeling. An emotional state is a state in which we are. This state has emotions, but the state per se is not an emotion. It's a combination of emotions in time. So you see, your concepts are not in your domain. And relations, you say, has positive expectation of A, B. This A is probably a human. A human has a positive expectation of something, and this B is maybe a goal. I have a positive expectation that I will succeed in doing something. And you see that your A and your B are not in your domain. So same error as Camille. But otherwise, it's a nice approach of giving domain, concept, and relation. Now, Julian says, in human psychology, hope is an emotion which expresses an optimistic expectation. Okay, that an imagined state will become reality. That's a nice definition, but it doesn't give me the domain. Concepts, emotion, current state, imagined state. Okay, and relation is a, contains a, sentiment. So is a and contains a are indeed relations you find in ontologies. Sentiment is maybe not a relation, but an attribute. But it needs some refinement. Kasi Islam says, in the domain of feelings, concepts, positive, future. Well, this is a bit superficial. Hope is in the feelings domain. It's a positive feeling that's related to what will happen in the future. Yes, but this is not part of your domain, so you're missing something. Julien gives an empty answer, so maybe he has no hope. I hope he has hope. And Johan says the word hope can be used as the main idea. Well, this is not an answer. This is not an ontology. Mathieu, l'ontologie est aux données ce que la grammaire est au langage. Well, I don't know where you found this quote, but I disagree with it. So, of course, it's a matter of definitions. So what do we call grammar? There are many, it's a polysemic word. So people have, in everyday language, grammar has some meaning, and in linguistics, it has another meaning. In linguistics, grammar is mostly connected to syntax. Okay, when we used the formal grammars, it was mainly for syntax, even though morphology can also be described by a formal grammar. Ontology is about semantics. So an ontology gives semantics to the data. This is already information, does give semantics, but ontology is classification, ontology is relation between, and these relations are not only hierarchical. So ontology goes well beyond syntax. Domain, désir d'un monde, une situation meilleure. So this is not a domain in the sense of logic. This is description or an explanation or a gloss of what hope is, but it's not a domain. Venkatesh says hope is subjective. Okay, he gives an example. I can build ontology with hope belief. If the reader does not, then this ontology is useful only for me. I think you have to revise the notion of ontology. An ontology is in a domain we define concepts and the relations between concepts. Here, whether a reader hopes or doesn't hope has nothing to do with the ontology, which is a definition of how we use the word and the concept ontology in human communication. Vanessa has a very nice answer. So concepts, she takes hope, person. So you see this was missing in the previous answers. Quality, success, sentiment, realization, desire. Relations are, is, are. Hope is a sentiment. Hope is a person. So maybe she's wrong here. Maybe she means a person has hope, or maybe she means a person is a hopeful person, so has hope in general, has the habit of having hope. Person quality, quality brings success and courage. So this is a very nice answer. Now, none of you has mentioned why we need this ontology and what would be the possible usages. An ontology, as we consider it in this class, is a computer-related resource. So it's not something philosophical. Well, it needs philosophy and psychology and so on to be established, but once you have created an ontology, it becomes a resource for computers, for machines, and an ontology of hope would be useful for a computer either to analyze some text or for acting in the world. Now, this morning, based on your answers, I have prepared a small sketch of ontology of hope for you. It's really something I did in just a few minutes without a lot of thinking. Let me give you first another resource I didn't mention yet, which is important. It's a resource called Wikidata. So I don't know whether you have heard of Wikidata, but Wikidata is a kind of very big generic ontology where you have lexical representations, words, and identifiers. If you look for hope, there are many things called hope. There are many towns called hope. There's the actor Bob Hope. And here you have, with this identifier Q19507, hope defined as an optimistic attitude of mind based on an expectation of positive outcomes. So this is just an explanation so that we as humans know this is what we were looking for. This is the right node in this big graph Wikidata. You have also explanations in other languages, and we will compare them in a moment. And here is a beginning of ontology. So I'm not saying, again, that this is the absolute truth, but it's a starting point for you. And it says hope is an instance of positive emotion. And here, when you see positive emotion here, it means that you have a node that again is connected to other nodes, be it in psychology, in sociology, whatever. Hope is part of psychology terminology. So you see that when we say instance of positive emotion, we mean, we talk about the meaning of hope. And when we say part of psychology terminology, we mean the term hope. And when we say term, we mean both the word, but also the concept behind it. And it is something studied by psychology. And then you have an image representing hope for some reason. And then you have pronunciation in German, okay? Then, and this is important, opposite of despair. So giving the opposite of hope is also a way of circumscribing its meaning. It is different from Speranza. This is probably the name of something, and here you have another node without explanation, and said to be the same as, and then here you have another link. So this is a bit technical. And then you have identifiers of the node hope in different other ontologies and resources. Okay, and here you have lexical representations in many languages. So this can be a starting point. Now, the other starting point is to look at definitions, but really technical definitions, not poetic definitions. And here you have the English definition: optimistic attitude of mind based on an expectation of positive outcomes. Now, you can look at this word by word and consider whether all of these words are necessary. An attitude of mind, okay, there can be attitudes of body, attitudes of mind, attitudes, there can be other types of attitudes. So attitude of mind is important. Based on an expectation is important because you have attitudes, other kinds of attitudes other than based on an expectation. Of positive outcomes is important because if the outcome is negative, then it's not hope, it's pessimism. Is the word optimistic necessary? Well, if your attitude is based on expectation of positive outcomes, then necessarily it is optimistic. So this is redundant. So maybe we don't need the word optimistic if we want a really mathematically precise definition. If you look at the French definition, there is no word optimistic. It's disposition de l'esprit humain, okay, so it's only for humans, qui consiste en l'attente, so based on an expectation, d'un futur bon ou meilleur. Okay, so this is just rewriting positive outcome in positive, good or better, so absolute or relative. If you look at the Spanish definition, it's quite different. It says creencia. So it's a belief, not an attitude. En que un deseo se realizará. So it's not about any outcome, it's a desired outcome. A desired outcome will be realized in el futuro, which is, okay, also a bit redundant because you also already have a future, realizará. So it's in the future. So this is a bit different definition and will give something different if we model it. And in German, zuversichtliche, so this means confident, innerliche Ausrichtung, so this is the state of mind, gepaart mit einer positiven Erwartungshaltung, so combined with a positive outcome expectation. So the German one is a bit more complete. It says we have two things. We have an emotional state, which is confident. It's even more precise than positive. It's confident, and it's combined with expectation of something positive in the future. Okay, and one can expect other, and we have other languages, which I will not translate. Most of them have no definition. Sometimes there is a definition, but there are a few of them. Okay, so this can be a starting point for an ontology. Now, what I have prepared for you is going a bit beyond the starting point. So I've used graph representation. I've put the concept of hope in the middle. And on the top and left part, I have cultural information. So on the top, you have a picture that is allegory of hope. So it inspires hope to those seeing it. Then I have lexical representations: hope, espoir, Hoffnung, Nadezhda, a very beautiful woman's name, Elpida in Greek, Al-Amal, and the Chinese one. These are lexical representations. There are many of them. You may have color symbolisms. In the US, it's rather yellow. In Europe or in China, it's rather green. A pictogram, and this pictogram does not have exactly the same semantics as hope. It also means good luck, but it's maybe the pictogram that comes as close as possible to this abstract notion. And then I took over here what was in Wikidata, so the opposite of despair, positive emotion, psychology terminology, and positive emotion is also part of psychology terminology, so I forgot to write it here. And I took the definition given by Wikidata. I omitted the word optimistic, and hope is an attitude of mind based on expectation. It's the case where the expectation is positive. So this is an hyponym. And this is a special case of attitude of mind, and this is a special case of attitude. Okay, so this is very brief, but it gives you an idea of, first of all, in an ontology, you can put many different kinds of information. It doesn't matter. It can be accumulative. Secondly, you put concepts which can be useful in specific tasks. So, for example, if a machine, so like a chatbot, has to analyze a sentence like, I hope you are well, or I hope this will work out. Here, if this chatbot, if this machine, this robot has the notion of attitude of mind or emotion, and this is something that can be programmed in the sense that I can say that I have a state, some kind of table, some kind of matrix, and this state models attitude, and attitude is needed for programming the next move, for controlling interaction with the outside world. If I have this model of attitude, then hope is a specific attitude with specific characteristics. So in that case, the machine will understand what it means. I hope it will work out. If again, you have programmed emotion, again, there is a link and the machine can use this link for analyzing. Same thing for interaction between the robot and the real world. If it has attitudes of mind and emotions, this is not necessary, but it can be done because this brings the robot closer to the human and allows better interaction with humans. Then here we have the necessary structure for the robot to, some will say to mimic, and some will say to simulate or to obtain this notion of hope. Okay, so I already took a long time on this, but it's because this morning we will talk about ontologies, and I would like you to really understand what an ontology is, how it works, and we will see in a moment how it can be used practically. So let's switch to the second question, which is quite different. The second question was about simplification.
Excuse me, sir. I answered this questionnaire this morning, but we can't see my my response.
Your what? Your response?
Réponse.
Your response?
Yes, I answered this morning, and there's no there isn't my response.
Ah. Yes, but 12. Indeed. Well, that's why I'm asking before 10 o'clock in the evening. Okay, so
Okay,
your
sorry.
answer is, where is it? Why don't I see it? No, this one I didn't mention. The Min Qian, state of mind. Ref D, state of mind, emotion, feeling. Ref C, ref R. Hope, optimism, joy, despair, helplessness, give up. Well, I don't really understand what this formalism is meaning, but this is okay. State of mind, emotion, feeling. Indeed, three different ways of considering emotion. Hope, optimism, joy. These are other cases, and despair, helplessness, giving up. Okay, and these are opposites. Yes, that's okay. Okay, so thank you for your answers, and let me switch to the next question, which was about simplification. Now, you gave me many answers. Most of you mentioned lexical simplification, and Venkatesh even gave the example of Charles K. Ogden, who defined simple English with only 850 words. So indeed, lexical simplification is the first step. It's an important step, because if you can replace a difficult word by a simpler one, keeping more or less the same meaning, then you can access a larger audience. Julian mentions synonyms, and indeed, for this replacement, you would like to have the same semantic field, but this is never really possible. There will always be denotations and connotations which will differ, but okay, this is the price to pay to simplify a text. Now, Camille mentions reducing the size of sentence, and others also give examples of breaking down complex sentences. So this is simplifying syntax, which is also very important. But as we see in this example by Julian, sometimes when you break sentences into small parts, you need pronouns to make links, to build links between the sentences. And this, again, can be a burden. So it's not, it won't necessarily make understanding easier. It's something that has to be balanced. So if a sentence written by Proust is 10 lines long, then of course, first thing to do is to break it in smaller pieces, but then the pieces have to interact correctly. And some of you are mentioning indeed the connections between broken sentences. And this sometimes also needs interpretation. Then Kasi Islam says lemmatizing stemming words. So this is done by the machine, but it's done when the machine has to apply some task, apply some algorithm. It's not for humans. You will never stem a text and give it to a human to read. And same thing here, no conjugation. If you don't conjugate your verbs, then it's pidgin English. It becomes hard to understand. So I guess Kasi Islam means avoid difficult conjugation, avoid futur antérieur, subjonctif passé, etc. So, but you have to conjugate, even though you can use more simple tenses than what is in the original text. Okay, and Nathan says we could use pictograms like Subing. That's a very good idea. But it has the disadvantage of making the text more broad to interpret. So you are adding generality and you are losing precision. Mathieu says we can delete unnecessary information such like adjectives and adverbs. So, okay, this is a good idea, but again, it's not something to do massively because sometimes it's the adjective that carries the information. So in fact, what you need to do first is find the point of emphasis in each sentence, and then you can remove whatever is auxiliary. But first you have to find out. So sometimes it's the adjective that makes all the difference in the sentence. And okay, Vanessa says short sentences, okay, and change words. Okay, so most of your answers are fine. You have concentrated on lexical simplification and syntactic simplification. Then there is also, maybe you have mentioned it briefly, but there is also semantic simplification. Semantic simplification means it's not just replacing a term by another term, it's choosing a concept which is easier to understand or describing the concept and keeping only the description. The purpose of this question was to make you think of complexity and how complexity can be reduced, and also the secondary effects of such an operation. So losing precision, maybe changing the meaning. And I have placed on Moodle a book that is entirely dedicated on simplification. So here you have two books. This one is pirated, so please do not distribute it. This one is freely available, so this one is legal, this one is illegal. And the whole book is about text simplification. And it has tons of algorithms and publications with evaluation and so on. And as I said many times already, never forget evaluation. So if we simplify text, how do we evaluate it? What are our goals? Goals are being simpler, keeping the same meaning. How do we evaluate these goals? And here you will find answers to these questions. Okay, and the next questions will be, and please, this time, it's the last time I'm asking questions, so please answer them, will be in this class, what was the part you liked the most and what did you find the most difficult? So pleasure, difficulty, and can you think of questions that would surely reveal a computer in a Turing test? And if you don't know what a Turing test is, I have a link to the Wikipedia page. So this is for thinking and give me some nice ideas. And this is a mandatory question. I needed to know your reactions because I can see you. I only see a screen. I only see myself on the screen. So I would like to know I would like to have your feedback on this class. Okay, so let's start today's class, which is a lab. You can find it on Moodle. It's about a question answer system based on ontologies. And the good thing with this lab is that it goes really from start to end. At the end of the lab, you really have the Python code for analyzing one question and generating the appropriate answer. It's very simplistic, but it gives you all mechanisms. The technologies we will use will be all ontologies, RDF triples, and Sparkle queries. So this are maybe not the most elegant technologies compared, for example, to conceptual graphs, but they are the most widespread ones. So if someday you will do ontologies and queries in your work, then most probably you will use these technologies. Okay, so we start with an ontology which you can find on Moodle, which is about wildlife, so about animals of the jungle or animals of Africa. And before starting the computer-related part, let us do some abstract modeling. So we choose the formalism of description logics, And we would like to model these sentences, which will be part of our ontology, in description logic. So animals and plants form classes. Classes in the sense of description logic. So this will be animal is a subset of the domain, and every subset of the domain is a class by definition. And plants are a subset of the domain. Trees are a type of plant. So trees are a subclass of plants. Tree, subclass, so it's square because we are in description logic. And we like to change the symbol so that it's not set theory, it's description logic. But it has the same name, subset or subclass of plants. Branch are parts of trees. Now, being part of doesn't mean being a subset of. It's stronger. Now, there are two possible. I'm defining a relation I call is part of. So in description logic terminology, this is called a role. It's a binary relation. A is part of B. So a hand is part of the body, of the arm, and the arm is part of the body, and so on. The head is part of the body. And here I'm giving you two different formulas. So remember the difference between those two. The first one says, among those who participate to is part of relation with a target being a tree, branch belongs, so branch is an individual that participates to at least one relation is part of, with a tree being a target. And the other one says a branch is an individual such that either it isn't part of anything or it is part of trees. I think the second one is most appropriate for us because a branch has to be part of a tree if it's part of something, or if you have broken it and now it's a standalone branch, then it's not part of anything. But again, you can say that historically a branch has been part of a tree, so it must have been part of a tree at some time. So both are more or less appropriate. Carnivores are exactly those animals that also eat animals. So this also means that they can also eat other things. So carnivores are exactly, so the exactly means that we go in both senses. So they are animals, intersection with individual that eats at least an animal, at least one animal. So this says that carnivores eat. The proof is they eat at least one thing, which is an animal, but they may eat also other things. And they are animals. And of course, they may eat other things than animals. Leaves are parts of branches. Again, same reasoning than before. Leaf is a subset of either those who are part of a branch, or those who are not part of anything, or are part of only branches. Giraffes are herbivores and eat only leaves. Again, but here I change this. I use a universal restriction saying that giraffes either don't eat at all, or they eat leaves and nothing else. So whatever, when they eat something, it has to be leaves. So you see the difference between these two formulas is that here I have that also eat animals, so they may eat other things, and here they only eat leaves, so I have here a universal restriction. And what this formula leaves open is the fact that maybe they don't eat anything. So if we want to be sure that they eat something, then we can add this. There exists a successor of eats with, we could put the whole domain as a target. And then in that case, it would be giraffes are herbivores that eat, and when they eat only leaves. Herbivores are animals that eat only plants or parts of plants. So a herbivore is an animal, and either doesn't eat anything, or when it eats something, it's either leaf or something that is part of a plant. So you see that my formulas become more and more complex. Lions are animals that eat only herbivore animals. So a lion is an animal that either doesn't eat anything, or when it eats herbivores, and herbivores have already been defined here. Plants are a disjoint class from animals. So this is something you have to say, otherwise one could expect something to be at the same time a plant and an animal. Edible plants are plants that are eaten by. Now, for the moment, is eaten by and eats are two different relations, but I can and I will define is eaten by as the inverse of eats. And they eat both carnivores and herbivores. And finally, I have three named entities, Leo, Gigi, and Giginou. Leo is a lion, and Gigi and Giginou are giraffes. Here we are in an open world. So we can have truths which are not stated. Nothing is done to prevent Leo from being a giraffe and a lion at the same time. So question, how can we avoid this? Well, by writing lions and giraffes are disjoint sets. Now question, can we show that lions eat giraffes? In fact, no, because we know that lions eat only herbivorous animals, okay? We know that giraffes are herbivorous animals. So potentially they could eat giraffes, but we don't have any proof that they do eat giraffes. So saying that a lion eats herbivores and giraffe is a herbivore doesn't mean that giraffe is necessarily eaten by lions. It's potentially, but if I take a given giraffe, then it's in the set, but not necessarily in the target of this set. Okay, now I invite you to download a program called Protégé, developed in Stanford. And I have prepared an ontology for you in XML. I could have used other formats, but I like XML very much. And you can open it with this program. So let me do it. Da, da, da. So Protégé is a free program, so it's not, its interface is not very user-friendly. It's a bit rude, but well, what can you expect from a free program? And what is it? Just a moment. Voilà, Protégé. Just a moment. Okay, so what you see now is the initial screen of Protégé, the initial window. So here you have the internal name of your ontology. So this is the official name of the file, wildlife.ol, but in fact, this is here the path, and this is where this ontology is stored in an XML file. Okay, this is the version of the ontology. Here you have some statistics, and most important parts of this window are these buttons here. Tac, tac. Now, for example, here, ontograph, and if you don't have this, you can load it going through check for plugins. You can add plugins. And this gives you a graph view of your ontology, which sometimes can be quite useful. Okay. Now, you have entities. Entities are classes and roles. Roles are called object properties. Classes are classes. And then you have individuals. And you also have individuals by class. Okay. So these are the two most important windows, entities and individuals. Now, entities, if I look at my classes, I have the generic class, all thing. Everything is a thing. So this is the top of the hierarchy. All nothing, the empty class. And then the classes I have defined. So to define a class, I click here on add subclass. So for example, if I want a subclass of thing, I will activate thing and click on add subclass. And then I have to give the class a name. This name is actually an ERI, International Resource Identifier, where the prefix is, so here is the ERI file wildlife.ol. So it's something local. It's not, it doesn't belong to a namespace. Hash, animal. So this is the name of this class. And this is the identifier of this class. Here is a comment I've written. This is for humans. And here you have properties of this class. And for example, at some time I said animals are disjoint of plants. Okay. Branch, I have defined the role is part of. How did I did that? I went to object properties. This is the generic object property, which doesn't mean anything. It just exists. And these are subproperties of the generic one, and one of them is part of. Here I can give properties of my property, so of my role. Is it functional? Is it inverse functional, transitive, symmetric, asymmetric? So if you don't remember what these all mean, it's easy. Think of mathematics. What is a function? A function sends one thing to one thing. Okay, so being functional means that for a given predecessor, I have only one successor. Okay, think of binary relations as pairs of predecessor, successor. And a function will send the predecessor to only one successor. So this means being functional. Inverse functional is the other way around. For each successor, you have only one predecessor. Transitive means if I have A sent to B and B sent to C, then I must also have A sent to C. Symmetric means I have, when I'm sending A to B, then I'm also sending B to A. Asymmetric means I have never a symmetric pair. So when I send A to B, I cannot possibly also send B to A. Reflexive means that for every A, I send it also to itself all the time. So equality, for example, is reflexive since every individual is equal to itself. And irreflexive is a relation which is never reflexive. Okay, so you see it's quite easy. And this is something I can add. Now, once I have defined the role is part of, I go again to the class and I add here this relation. This is to say that branches are parts of trees. So I click on this cross here. So I guess now you don't see this additional window which has opened. It's just an editor window and I can type is part of sum and tree. I type them and once it's recognized, it changes color. And once I have three things, is part of sum tree or only tree. So sum will be the existential restriction, only will be the universal restriction. Then I click on save and I obtain this branch being subclass of this. Sometimes it's easier. Carnivores are simply subclasses of animals. So here I just type animal. And lions are subclasses of carnivores. And lions eat only herbivores. So once again, I type on plus here and I write down eats only herbivore. Then here I can add individuals. So individuals here, there is no hierarchy. I just click here to add an individual and here to delete an individual. And once I have added an individual, I can assign it to one or more classes, and this is called type. So Gigi belongs to the class giraffe. And Gigi is different than Gigino. So here I can say which individuals are the same and which individuals are different. And then here I can add property assertions. So if I have defined the role eats and the role is eaten by adding them here to object properties, and by saying that is eaten by is the inverse of eats and eats is the inverse of is eaten by, then here I can add an object property assertion and say that Gigi is eaten by Leo. And I can also add attributes. These also have to be defined in data properties. I can define weight and, for example, size. Oops, this was a mistake. I wanted it to be an independent one, so I activate this one and say I want weight, size. And now I have this property and I can add it to individuals. Okay, so this is the part of protege interface which we will use to create and edit ontologies. So let me return to the lab. Okay. Now, Protege works with reasoners. A reasoner is an inference engine. It's a program that will take statements in an ontology and create new statements. Some statements will be created automatically, others will be created upon request, so upon a query. To activate a reasoner, you go to, so in Protege, to the menu reasoner. You have the choice, at least on my Mac, I have the choice between Fact Plus and Hermit, or I'm using Hermit. You may add other reasoners, there are many of them. And once you have activated and started a reasoner, you need to click on Command R. So on the Mac, it's a command, or I guess on Linux, it's a control, to synchronize the reasoner. So synchronizing means that the reasoner will inspect all of your statements and tell you whether they are coherent, so logically valid, and maybe create some new ones. Now, there is a tab called DL query. So database language query. And there you can type queries and obtain results. So let me return to Protege. Voila. Oops. Sorry, voila. And this is the top DL query. And now I can type here a query. What is part of some tree? Execute. And it replies branch. Because I said that branches are parts of trees, so is part of some tree will reply branch. Now what I can do is add in an individual, which I will call branch. It's a diminutive of branch. And I would say that this individual is a branch. Just a moment. Sorry for the interruption. So I was saying that branch is now a branch. And if I go again to DL query, I synchronize my reasoner with Command R. You see that this same query gave me also branch as an individual being the result of this query. So you see I get both classes and individuals. So you see already a big difference with databases. In databases, you have only individuals. Here, you can reason with classes and with individuals. Okay, now let me add a fact that will be contradictory. So the fact will be Gigi eats Gigino. So this is a kind of cannibal giraffe eating other giraffes, a zombie giraffe. So I will go to entities, individuals, Gigi, and I will add here eats Gigino. So you are not seeing this because it's a separate window, but it has two fields, and I put eats in one and Gigino in the other. So you see, this has been accepted. Gigi eats Gigino. And now I type on Command R, and I'm getting a window, which you don't see, says inconsistent ontologies. And I have a button, explain. And when I click on this button, I get a window that I would like to show you. I hope it will be easy to find it. Yes. There we go. So now you see the fact that my ontology is inconsistent. And as a result, it gives me some statements in the ontology. So in the lab support, I have a screen copy of this explanation. And I have here the proof that you need every one of these facts. So if I take number 3, Gigi is a giraffe. And number 6, giraffe eat only leaves, then I get by modus ponens that Gigi eats only leaves. The contradictory statement is Gigi eats Gigino. It's number 5. And if I take number 4, Gigino is a giraffe. Number 6, giraffes are herbivores, or maybe 7. I think I missed one here. And herbivores by number 1 are animals, and animals by number 2 are disjoined with leaves. So taking those 4, I get that Gigino is not a leaf. Okay, it may sound trivial to a human, but for a machine, it's not trivial at all. We have just proven that giraffes are not leaves. And if
Un diablo se cayó al agua y otro diablo lo sacó.
Okay, so Gigi eats Gigino and Gigi eats only leaves and Gigino is not a leaf. Oops, modus tollens, contradiction. So we need all of these statements as a proof why the ontology is inconsistent. So you see, protégé will protect you from inconsistent ontologies. Now, before we stop for a break, some easy stuff, complete information by adding properties to these is part of eats, eaten by. Are they functional? No, we can be parts of many things. Are they transitive? Yes, is part of, is transitive most of the time. So let's go back to protégé. So let me remove this bad assertion it's no back. And let's go to properties. So is part of, I can say, okay, it's transitive. And now I type on command R, and you see immediately I get that a leaf is also part of a tree. This arrived when I said that being part of is a transitive relation. Is it symmetric? I can, this is a choice. I can say that I am a part of myself or not. Is it, no, sorry. Symmetric means is A, if A is part of B, then B is part of A. No, definitely not. So we can say that, we can even say that it's fundamentally unsymmetric, asymmetric. So is part of is asymmetric. Will this change something? Internal reason or error. There's somewhere an error. So maybe we have to think about this a bit more. Is it reflexive? Not necessarily. Irreflexive depends. And so on. We are not obliged to answer all of these. And then I'm asking to put some additional information. So on weight and size, this is easy. I just defined size. So Gigi is 5.80 meters. So I add here that I want the data property size, and I have to give a value. The value will be 5.80. And I can even give a type. Type in the sense of XSD, XML schema language types as a decimal number, and so on. So I will take a break now. I hope you are comfortable with Protégé. As I said, it's not the most user-friendly program that exists, but it's robust and it works well, even with big ontologies. And it has these nice reasoners. And also you can use Sparkle inside Protégé, as we will see after the break. So we will continue. Now it's 10:48. Let us continue at 11 and 5 minutes. So see you in a moment. In this part, we will process the ontology using Python. So this is quite innovative, and up to now, people will, oops, sorry, bad screen share. People would mostly use Protégé and tools like that to work with ontologies. And we will use some new tools based on Python. So you will have to install many things. Stanza is a natural language processing kit, which is much better than Spacey. But it takes some time to download because for each language it will use corpora of many hundreds of megabytes. So, for example, for French or for English, I think the corpus is around 600 megabytes, so it takes some time to download it. Okay, this little program is already on Moodle, and it says get ontology. So here should be -en.xml. So this is really the file name. Load, it loads the ontology. And I forgot to change this into English. Sorry, the solution is correct. On Moodle, you have the English version, but here I left the French one. Okay, so here are the classes, here are instances, here are roles, here are attributes and individuals. So the object ontology has many methods, and you have methods corresponding to each ingredient: classes, roles, attributes, individuals. And here are the results. So when I'm asking for classes, I get on property, all values from, union of, and nothing. So you see, these are hard-coded classes. This is why they have the prefix all. And these classes here are the ones of my ontology. So this is the file name, and this is the class name. So predefined hard-coded all classes are also classes of the ontology, as long as they are used somewhere. Instances of classes, you have on property, all values, union. You have instances in the ontology, and then you have instances of the class animal, and this is the ERI of the individual Leo, and this is Gigi and Gigino. Then here are subclasses with individuals. Here you have roles, Now, the role eats, here I've put the domain and here the range. So for eats, in the ontology, we have given the domain, animals eat, but we haven't specified the range. So the range has not been specified. Same thing for is eaten by, is part of. Attributes, and then properties of individuals. So by asking here, for each individual in ontology method individuals, get me the properties of the individual, and for each property, give me the value of the property for this individual. So here prop is a dictionary indexed on the individuals. Give me the value. And here I'm using the Python name of the property. And here the value of the property for the given individual. And this is why here you see the individual Gigi, and the property is eaten by value Leo, and weight value 800. Okay, so this is just one way of exploring the ontology. Now, you can use this for searching, but it's not very powerful. You have something better. You have the method search. And in search, you can use either identifiers or types or subclasses or property names. So this is a quite powerful method. Here are some examples. And this again is a file on Moodle. And this time I have the correct file name and it's in English. So this is what we had already onto classes. And here I start searching. So my first search is find me those individuals having this ERI. Now, this is a class. Why am I using a star here? To say that I don't care about the prefix. I want the name of the class to be animal. And the result will be class animal. Okay, so it's not individuals I'm looking for, it's classes I'm looking for. A class of ERE animal. So if I had other animals in other, with other prefixes, I will get them as well. Here I'm using the star as a joker to get all classes ending with plant. So the result will be plant and edible plant. And you see in the results, I always have the complete ERI, prefix and name. These can be nested. So I can say, find me subclasses of the class animal. I first have to find the class animal. Find me among all classes of name animal, take the first. I know there is only one. And use this in a new search for subclasses. Find me the individuals of the second subclass of animals. So first I'm looking for all classes called animal. Then I'm taking the first of them. Then I'm taking all the subclasses of the class animal, and I'm taking the second subclass, and then I want individuals, so the query will be type equals to this. So this is a class, which is the second subclass of the class animal. So you can see you can nest your queries arbitrarily. Find all animals, so find all individuals, all those who are of type class animal. And since there can be many animal classes, I want the first one. Find all individuals weighting 800, weight equals 800, and these are necessarily individuals. Find who eats GG. I want each to take the value of the individual GG. So here you see I have again ERI, but since this is an individual, what I get is an individual. Find who makes what with whom. I take all individuals, I take all properties, and if the individual is participating in a property, in a role, then I'm taking the value of this. There may be many of them, so again, a for loop, and I print the individual, the role, and the successor, the value. And here are the results. Just a moment, my computer is very slow. Who makes what with whom? Wildlife all GG is eaten by wildlife all Leo. And Leo eats GG. Okay, so this is a bit more sophisticated way of doing queries. But it's still not powerful enough. It doesn't have the representative power of a query language like SQL. So you can use this as a first approximation, and if you need something more powerful, we can switch to Spark. Now, how can you use this? Our goal is to make a question answering system. So if a given question you receive, you can interpret it as a query, then here is how to send this query to your knowledge base and get results, and then you will have to convert the results into natural language. So this is the part of querying the knowledge base. To be more powerful and to have the opportunity to use an industry standard, let us move directly to Spark. So Sparkle is today the top knowledge base query language. It has a bit peculiar syntax. The syntax is as follows. You first write all of your prefixes, because every ERI you're using has to be in some included in some name, in some namespace. So these are namespaces, and these namespaces are attached to, Voilà. And these namespaces are mapped to prefixes. and in the remaining, we use the prefixes. Now here you have a query that looks like an SQL query. Select where. After select, you can use one or more variables. Variables always start with a question mark, followed by some name. And here you have RDF triples. So you see you have 1, 2, 3 items and a period. This is the this is the subject, this is the predicate, and this is the object. So the conditions, the constraints you impose to your variables are always written in RDF triples. Here the predicate is type in the RDF namespace, and type means being an instance of some class. So I'm looking for the individuals who belong to the class lion. And lion, I have used the prefix me, which is the one of my small ad hoc ontology. This will give me all lions, all individuals of the lion class. And if I want giraffes weighing more than 750 kilograms, I will use 2 RDF triples. I want giraffes, and they have to have a weight. So I'm attaching the weight of this giraffe I'm searching to the variable weight, and this weight has to be larger than 750. So you see here, I have an internal variable which doesn't appear in the select statement. Now we can play around with Sparkle inside Protégé. Let me go back to Protégé. Voilà. Now, in Protégé, by default, you have a tab called Sparkle. You shouldn't use that one. You should go to create Windows, create new tab, views, query views, snap Sparkle query. So once you have found it, it will remain on your interface. And this one is better because it uses a reasoner. Now, here you can type your Sparkle query. It will get syntax colored. So these are my prefixes, and here's my select question B, where B is of type animal. And for animal, I have a prefix me, which is my file. So this is the name I gave to my the ERI of this file, which is not necessarily the name of the file on disk. As you can see here, the name of the file on disk is wildlife-en.xml, but I gave it the symbolic name wildlife.own. Okay. Execute the query, and I get nothing. Why do I get nothing? I had to synchronize the reasoner with Command R, and now I get Gigi Leo Gigi. Okay, so here you can play with Sparkle queries and get used to the syntax. Let me return to the lab. Now, how do we use Sparkle under Python? I will use the package Sparkle, and more specifically the class rdflib plugins. No, sorry, the package is rdflib, and it has a Sparkle plugin which I will use with the prefix Sparkle. Now, here there's a small technicality. In already, onto what I get from get ontology is an ontology object. And I can use this ontology object to make queries in DL, as you have seen. But now I want to use Sparkle. Sparkle works with RDF triples. Onto is an object. It doesn't have RDF triples. So I use this here, default graph dump, and so this will take the ontology. So I don't remember exactly how it works, but it will take the ontology and will transform it into a graph of RDF triples. And this is the object I get, which this time is a graph of RDF triples. And I will prepare a query, as is very often the case in Python. When you use query languages, you prepare a query, and then I will submit this query through the query method to the graph, and I will get results. Here my query is exactly the same as before. Find me all the lion individuals. Now we need here a small function, Python function, that will distinguish between IRIs and other kinds of objects. And if we give this function IRI, it will return the string, so the name of the IRI. Okay, so this is just for cleaning up the results to make them more human readable. Now there's another thing. It's the fact that the reasoner will do some inferences, but not all of them. So, for example, the reasoner will do all the inferences necessary to get your result. But if you have declared a role as being transitive, then the reasoner will not apply this transitivity automatically. So, for example, if I ask the query, what are the subclasses of animal? I will get only the direct subclasses, not the subclasses of subclasses, even though we know that subclass is a transitive relation. Now, to avoid this, we can use a star after subclass, which means that this will be a closure. I will take the transitive closure of subclasses. So here are the results of this query. Animal, so itself is a subclass of itself. Carnivore, lion, herbivore, giraffe. And you see that lion is a subclass of carnivore, which is a subclass of animal. And here I have some examples of Sparkle queries. So this one says, find the class animal. So I'm looking for individuals of type class. So this means that B is an individual. So this line says that the variable B is a variable of individuals. No, sorry, no. This line means that B is a class. So B is a variable of type class. Sorry for the misunderstanding. So B is a variable of type class, and I'm looking for all B's called animal or having animal in the name. And the result will be file wildlife all hash animal. The second one is none. So this none comes, I guess, from I don't know where it comes from. It's a second answer which is not valid. Okay. Find all classes that end with plant. Same thing here. I use a star in a regular expression. It's a regular expression, so it's dot star. And so I will get plant and edible plant. Find all animals. This time I'm looking for individuals. So my B will be of type named individual. I want only those individuals that have names. And B is of type X. So this time it means that it's an individual of this class. And this class is a subclass and eventually a transitive subclass of animal. So it can be animal directly or some subclass of animal. So you see that this type means both the type of my variable and the class to which the individuals that are values of these variables belong. And I get Gigi, Giginu, Leo. Find me individuals weighing more than 500 kilograms. Same things, but with two additional relations. The fact that I need an internal variable of weight and that this is the value of an attribute weight for the same B, and also size, an internal variable size, and sorry, with an E here, and here the attribute. The semicolon means that this triple is used, so the first part of this triple is used also for the second expression. So when you put a period, it means your triple is finished. When you put a semicolon, it means that you can write another triple using the same subject. And if you put a comma, then it means that you keep the same subject and the same predicate, and you have different objects. Another way of writing the same thing with a comma. So I want B to be of type X, but also of type named individual. Find me who eats Gigi. I'm looking for B such that B eats Gigi. Find who does what with whom. Here I have three variables: the subject, the predicate, and the object. I just need to say that B is a object property, and that I have this triple, A, B, C. And here's what I get. Leo eats Gigi, and Gigi is eaten by Leo. Okay, now you have plenty examples of how to use Sparkle in Python, and you have the complete code here. This is all you need. Starting from an ontology, send a Sparkle query to this ontology, and get the results. So this, I don't know if you realize it, but this is very simple and direct. Up to now, 10 years ago, one would use servers with plugins, and it was terribly complicated to send Sparkle queries to knowledge bases and get the results. Okay, and now at last we arrive at our main problem, which is the question answer system. So here are some questions we may want to ask. What are the something? So what, in the sense, give me the names of, I would have used who are giraffes, who are the giraffes, but I'm not sure whether in English we use who for animals, so I used what. But this is the idea. I want the names of all what? All animals, all plants, all lions, all giraffes, and so on. So my question is generically, what are the, and here a class name in the plural. The possible answers, there is no. So if I ask what are the antelopes, there is no antelope. What are the lions? There is a single lion, so the class name in the singular. It is the name of the individual, Leo. What are the giraffes? There are two giraffes, in plural. They are Gigi and Gigilu. So you see, this will be the input, and this will be the output after sending the query to the knowledge base. Other possible questions: is Leo a lion? Answer yes or no. We could, if it's a closed world, then the answer is yes or no. If it's an open world, then we can also answer I don't know. And what do we know about such an individual? And here we can give a collection of possible answers. So here, this is the general form of questions we want to consider. What is, what are the giraffes. So give me the names of the giraffes. In this implementation, we will use the package Stanza. Stanza is much better than Spacey. It has been developed again at Stanford by Manning. Some of you may have heard of Manning. He's a very well-known specialist of natural language processing, the statistical approach. First thing we will do is write some example questions. What are the giraffes? Is Leo a giraffe? What do we know about Leo? And see how Stanza parses them. So I'm importing Stanza for English. The first time you run this, it will take some time to download the corpus. It may take some minutes, but afterwards it will be immediate. I want to use this corpus, the English one, and for each sentence in this list of sentences, I am processing the sentence. I'm getting a doc object. And no, sorry, there can be more than one sentence in each text, but for us, each text has only one sentence. So for sentence in doc sentences, in our case, there's only one. For token in the words of this sentence object, I want token ID is the number of the word in the sentence, the number, the identifier of the token. Token text, so this is the occurrence. Post tag, universal post tag, pronoun, auxiliary, determinant, noun, punctuation. Features of the token, all possible features. So for our verb, we will have mood, tense, verb form, and so on. Lemma, so the lemma is the standard form of our token. So for the verb are, the standard form is be. For giraffes, in the plural, the standard form is giraffe, in the singular. Token head, so in my syntactic dependency relation, who is my governor? And this number is the identifier of a word in the sentence. And dependency relation, so what is the nature of the relation? So for example, here, what is a pronoun? What kind of pronoun? An interrogative pronoun. And it has no governor because it's the root of the sentence. You see, this is the typical example of a sentence, the root of which is not a verb. Because here, instead of a verb, we have a copula, to be, an auxiliary. And so it is the pronoun what, which is considered as a root of the sentence. Are is governed by what? The is governed by giraffes. Giraffes is governed by what? By what? The relation between giraffe and what is a noun-subject relation. The relation between the and giraffes is a determinant relation, and punctuation, again, is governed by what? And same thing for the other two questions. I get the results of my pause tag and syntax parse through Stanza. So this means that whenever you will write a question of this type, Stanza will make the same pass. So how will we analyze this? Well, imagine you get the question, what are the giraffes? You would like to classify this as one of the three kinds of questions we saw here. Well, you can ask, so you take this question, you analyze it, you pass it through stanza, and now you got your sentence object, you have your tokens, and if I get a token which has the lemma what, which is a root, and no, sorry, if you get a token that is a noun and is governed by a root which is the lemma what, then I can reasonably say that I got the type of question, what are the something? And this something is the token I have just found. Okay, so I'm looking at the tokens, and if I find a token that is a noun and is directly dependent of the root of the sentence, and this root is the interrogative pronoun what, then I'm sure that I got this kind of question, the question, what are the? Okay, now this is a bit simplistic, of course, but if you can tell your user to use only specific kind of questions, then you are building a controlled language. And in this controlled language, you can simply classify questions like this, and you can be pretty sure that you're interpreting the question in the right way. If your language is not controlled, if your language is really arbitrary, then it may be a bit more difficult. In that case, maybe a statistic approach like the one by Dialogflow is more appropriate. This means you will have less precision, but more recall. Here, we are taking the case where we can have an agreement, an implicit or explicit agreement with the user. We ask the user to write sentences of a specific type. And if we don't recognize the sentence given by the user, then we can ask the user to reformulate it. So this is an agreement, agreement we take in advance. And in that case, this will work. So we have identified the type of the question, and we have identified what the user is looking for. So user is looking for individuals of this kind. And the kind is the lemma of the token. I'm using the lemma because lemma is in the singular. Once I get this, I just need to write my Sparkle query. And the Sparkle query will be, what are the, and build Sparkle query. here is the query. Query of, I'm looking for named individuals of type X, where X are what I got from here. So maybe I'm missing something here, but you see how it works. Now, we will get results, and these results have to be supplied to the user. So now we need to do the opposite. We need to do natural language generation. So we take our results, we look at the length of the result. So here result is Python list, since we append namespace, we append ERIs, and we strip the namespaces. So here we have only the names of the individuals in a list. We look at the length of this list and answer in the appropriate way. And if we have many results, then we just do a join of these results separated by commas. Okay, so now in this small piece of code, you have, for a very simple case, for a very simple ontology, a question answer system. It only recognizes one type of question, but it will analyze the question, find what you are looking for, ask the ontology, get the answer, and convert the answer into natural language. So this is a very simplistic but end-to-end question answering system. Now, if you want to go further, then of course you can make more complicated questions, and your analysis of the questions can be more sophisticated. You can ask the user for confirmation. Are you asking this? Yes or no? You can classify the results so you can have more sophisticated answers. So for example, somebody asking, what are the animals of the jungle? You can say there are two kinds of animals, lions and giraffes. Lions are Leo and giraffes are Gigi and Gigino. So you can voluntarily add a step of classification. But then there's one thing which we have not explored and which is extremely interesting, is ontology feeding. Because what we haven't seen yet is that with Sparkle, you can also add things exactly as in SQL. You can add new concepts, new relations, new individuals. And this means that your chatbot can enhance, improve, populate its ontology, which of course is more difficult than populating a database, because your knowledge base has to be coherent. So if you want to add something, then you have to check whether it is conformant to the logic of the knowledge base or not first, and then you add it automatically, and then it will appear in subsequent queries by users. Okay, I have some references. The first reference is about OWL in general. The second one by Maria Kate is an article on African wildlife ontology. So the ontology we used with the lions and giraffes is paradigmatic. It has been introduced very early as an ontology example. There are two paradigmatic examples, this one and another one with pizzas. The one with pizzas is a bit too hierarchic. You have toppings, ingredients, and so on. So it's really a hierarchy of ingredients. While here, with wildlife, you have relations of eats, being eaten. It's a bit more interesting. So I've chosen this one. And Maria Keith lives in Africa, so she is doubly interested in that. And she has written a very nice book on ontology engineering. It's the one I've placed on Moodle. And then on the interaction between ontologies and Python, you have this very nice French book by Jean-Baptiste Lamy. Jean-Baptiste Lamy is actually working at INRA. So he is dealing with biology and medicine. So he is applying ontologies to drugs, to proteins, to all these concepts in biomedicine. And this book is very interesting because it's really from the user's point of view. It's a very practical book and it's very well written. And I haven't seen the same topic on in English books. So it's kind of innovative. Okay, so we can either stop here or maybe you have some questions. And if you want to go a bit further, then you can take the other type of question and try to implement it. Do we have any questions?
Monsieur? Allô?
Yes.
Ça n'a pas de rapport avec le TP, mais je me demandais s'il existait des ontologies disponibles sur des systèmes de pensée qui ont été développés par des philosophes, par exemple. Des choses comme ça.
I have a problem with my... Okay, so the question was, are there ontologies in what domain?
Le domaine de la philosophie, pour représenter les systèmes de pensée qui ont été décrits par des philosophes célèbres, par exemple.
Okay. In the human sciences, you have much less ontologies than in exact sciences. There are some attempts to start such ontologies. Now, the problem when you want to search for such ontologies is that the word ontology is polysemic, and the concept of ontology exists in philosophy and means something different. So when you type for ontology of philosophy, then you will not get a computer ontology of philosophy, you will just get the meaning of ontology in philosophy.
Oui, c'est pas très pratique.
think I found, yes, I think I found such an ontology at the University of Buffalo. So this is the XML file. So here, I think this is an answer to your question. Philosophy family tree as a linked graph. But I don't see the names. This is so wiki inaccessible. Tab list. Okay, so these are names of what? Probably philosophers. Okay, so this is just one application. Philosophy ontology. All version. Okay, so I think this is what you want. Foundations of an ontology of philosophy. Ontology building. This sounds already like a computer ontology, and formalization. Okay, and now this is definitely logical formalism. Domain relations, concepts, classes. So this is first order logic formalism, but I think then they convert this to all, and their philosophy is written in all.
Merci.
Okay, so there are probably other attempts, and then you should also look into the big picture of LinkedIn, no, not LinkedIn, linked data. Linked data. This is just an explanation, ontologies. I have to go to my lecture of last week where I gave, I have a slide with website where you can access ontologies, open ontologies. So maybe it wasn't in the linguistic, maybe it was in the formal thread. Voila. Let me share the screen. Yeah, so this is from the slides on symbolic methods. And remember this cloud of ontologies. So here you will certainly find also some ontologies on philosophy. And to find out, you just need to go here and make a search. Voila. And you see linguistics, life sciences. Well, there probably is one on philosophy, and if not, then take the one by Buffalo.
D'accord, merci.
And Tian says that the file wildlife is missing. Sorry for that. I thought I added it. Let me see. This is the 9th lab, and here are the files necessary. Okay, so here I did a mistake with Moodle. I added more than one files in here, but apparently you cannot access them separately. So I will make a zip archive, and that way you will download all three at the same time. I will do this in a few moments. It's weird because Moodle allows you to put more than one files, and then when you click on it, you get only one of the three files. Okay. Okay, so if you have no more questions, we will stop for lunch and start again at 1:30 with a short lecture on some deep learning techniques for topic modeling and embeddings and automatic summarization, and then exploration of some Jupyter notebooks. So, bon appétit à tout le monde.
Merci.